And I'm not sure if I'm live or not. If I go live. طيب السلام عليكم جميعا. Welcome back to continue our series on selected topics on radiation physics. And today we're going to start something I think everyone has been asking for it, interactions of photons with matter. The problem I faced preparing this session is I don't know how deep should I go in this. But eventually I said, look, I need to go a little bit deeper than maybe what most of you are. I don't know what you have taken in your graduate physics courses on these topics. But I said, okay, since I'm going to give this lecture, I think maybe I can add something interesting to all of you. So I might go a little bit deeper on some of the topics. And that's why probably I'm not going to be able to cover all the interactions of photons with matter in this session. Maybe next week, actually, I can do actually another session. So we will continue. We'll do another session next Saturday. Okay. So interactions of photons with matter. There are a number of interactions. Some of them are really important for us, especially in our field of, let's say, radiotherapy or imaging. But there are others that are also probably important in physics in general, or might come, of importance when we, in, for example, radiation and protection. So I thought maybe I'll just cover as much as I can, but I will focus more on interactions that are really, really important. So there are a number of interactions for photons with matter. The first one is photo effect. Then we have Rayleigh scattering. We have Compton scattering. And then we have nuclear pair production and electronic pair production, or it's known as triplet production. And another interaction is photonuclear disintegration interactions. Of course, I'm talking about interactions of ionizing photons. So let's be specific, ionizing photons, and because photons might interact when they have much lower energies with matter in different ways. But what's really interesting for us is the interaction of ionizing photons with matter. But there is one interaction that probably I would like to start with. Maybe many of you actually never heard of it. I believe it's good as a theoretical model for the other scattering interactions. Some say that actually this interaction could happen at very, very low energies. I still have a confusion on this statement because the cross-section of this interaction is actually higher than Compton, to tell you the truth. So still in megavoltage, we see Compton scattering, but we don't see this interaction. This interaction is called Thomson scattering. So what is Thomson scattering?
دكتور وميض البرزنتيشن مش طالع احنا شايفين بس
sorry,
حضرتك.
okay. I did not share this. Okay, so let's share it. دائما نبهيني إذا في حاجة missing. Okay, الحين طالع؟
نعم.
Okay. So the first interaction I would like to talk about is Thomson scattering. Who has heard about this interaction? Anyone heard about it for the first time? Okay. As I expected, this is probably the first time for all of you on this interaction. It's a very actually simple interaction. And classically, it has been derived. I'm not going to derive it, but basically, we have an electron and we have an incident photon. This photon has an energy of h mu. It has, it propagates with a frequency mu. And then what happens is that this electron, because the photon has, an electric and magnetic field, the electron will start to oscillate with the same frequency of that of the photon. So it absorbs the whole photon. It starts to oscillate in the direction of parallel to the electric field component of the photon. But what we have talked about last time is that whenever we have an electron undergoing acceleration, okay, because when it oscillates, okay, it's going to it's going to be accelerated and decelerated. So what happens is that this electron will emit radiation. It will emit a photon. And that photon, the frequency of that photon happens to be equal to the same frequency of the incident photon. So all what has happened is that this incident photon, when it interacted with this electron, it's a free electron, then this photon, we can think of it as being scattered at an angle. So it's going in this direction. Now it's going to be scattered at an angle theta. So these are the important points. Thomson scattering is an interaction of a photon with a free electron. In this interaction, the photon is scattered with the same energy. H mu equals to H mu prime. Therefore, there is no energy transfer to the electron. So the electron, after the photon is scattered, the electron will not gain any energy. By the way, just before we go through these photon interactions, what's really important, always, whenever we talk about interaction, we have to talk about what is this interaction. Okay, define this interaction. Another important thing is we deal with the energy transfer to electrons or to charged particles in general. Because later on, we want to calculate doses, how much dose being deposited in tissue for indirectly for a photon. So the photon first has to actually transfer energy, has to give energy to the electron. And then this electron will then later on deposit those in the medium. So therefore, it's very important always when we talk about photon interactions or ionizing photon interactions, we need to discuss the energy transfer to charged particles, because later on that will help us to determine the dose or absorb those in the medium. So in this case, for Thomson, also one other important aspect for photon interactions is, okay, whenever we have a scattering, for example, of a photon at angle, the question is this scattering equally probable, meaning that the photon being scattered, let's say, between 1 and 2 degrees, is it equal to the same probability of being scattered, let's say, at 90 degrees or backward at 180 degrees? So we always have to talk about the cross-sections of these interactions. The cross-sections, we will learn from them. For example, the scattering angle of the photon, the probability, we're looking at the probability. All possible angles, or angles, scattering angles are possible, but we want to look at, okay, where is the photon going to be likely scattered towards? That's one thing. And another thing is that when we start to compare the cross-sections of or probabilities of these interactions, we have to talk about the total cross-section of this interaction, because that's the only way to compare. Is, for example, if a photon is going to interact with, let's say, with media, is the interaction going to be Compton? Is it going to be photo effect? Is it going to be Rayleigh? And so on. Each of these interactions has a cross-section, and from these cross-sections, or total cross-section, we can then calculate what is the probability of this interaction to happen. Okay, so for Thomson scattering, the definition of this interaction is basically interaction of a photon with a free electron. What happens in this interaction? The photon is scattered with the same energy, and no energy is transferred to the electron. So this is energy transfer for Thomson equals to 0. So now we know the photon, based on this interaction, the photon is going to be scattered. The question, what's the angle of scattering? Or what's the probability of scattering angle? Is it likely? Is the probability, is it the same probability regardless of the scattering angle or not? Or there is a preference, for example, for a given angles or set of angles. This is so in order to answer that question, we need to calculate the differential electronic cross-section, okay, per solid angle. This is cross-section per solid angle or per angle theta. So there is a derivation actually in the book Radiation Physics for Medical Physics. It's a nice derivation. It's based on classical, it's a classical derivation. And at the end, what we get that the differential cross-section with per unit solid angle for Thomson equals to this constant Re is the classical electron radius. I really tried to look into why is it called the classical electron radius. Is it like in the past, based on some experiments, people thought the electron has this radius? I really don't know why it's called that, but there is probably a reason for that. But we know that the radius of an electron is not this value. It's much smaller than this value. A proton, for example, the radius of a proton is about 1 to 1.25 probably Fermis. And we know the electron is much smaller than a proton. So this is not correct, although this constant, it's actually, if you go and type in Google and what's the classical electron radius, it has this value, 2.82 Fermis. Okay? So if we plot this differential cross-section per unit solid angle, then the value, this is the plot of this curve. At theta equals to 0, it's just given by Re squared, it's 80, okay? And at the minimum will be at 90 degrees. When theta equals to 90, this value is going to be 0. So it's going to be Re squared over 2. Now this, maybe it's a differential cross-section, but we usually like to look at, by the way, I hope you're familiar with the barn. So the barn is a unit of area, usually used for cross-sections, and 1 barn equals to 10 to the power minus 24 centimeters squared. Okay, so here on this, the plot here, these units are in barns, or in millibarn, and a barn is 10 to the power minus 24 centimeters squared. It's a unit of area. Okay. What's really helpful, especially, I mean, for me especially, is I like to always calculate the differential cross-section per scattering angle, because usually we think of, okay, the photon being scattered, let's say at 1 degrees or 90 degrees or 180 degrees and so on. So if we convert using the differential cross-section per solid angle, we just take this d omega by d theta, and since omega is it's basically, we don't have a differential for the omega angle, then we get this formula here that looks like this. The formulas, don't worry about these formulas, but this curve, what does this curve tells us? This curve tells us that, okay, it's actually the highest probability. If we're looking at an angle, let's say per 1 degree, this is actually going to occur at 55 degrees and at 125 degrees. So a photon, so if a photon is undergoing a Thomson scattering, the highest angle, probability of an angle, it's going to be between, let's say, at around 55. So usually we take like half a degree or 0.1 degree plus or minus. It's around that value. And also at 125 degrees. This is actually the photon being scattered in a forward direction, and this is actually the photon being scattered in a backward direction. Okay, so imagine, so that we understand what's going on here. So now we have this photon, okay, and we have the electron here. So actually this photon, this angle, 55, or this angle, which is 125, are equally likely to happen. So if we send, for example, 1,000,000 photons here, and we end up by let's say 10 photons, I don't know the value exactly, but suppose I get 100 photons in this direction, I'm also expected to get 100 photons in this direction, okay, at 125. Another thing is that we want to see, is the photon likely to be scattered in a forward direction? When we say it's in a forward direction, meaning that the scattering angle is less than 90. So the photon being scattered with an angle less than 90. In the backward direction, the photon is being scattered with an angle greater than 90. And what we look at this differential cross-section plot, and all what we need to do when we want to deal with probabilities, we look at areas. So imagine we have this here. Okay. This. So all what we need to do is we look at this line, okay, and we look at this area. The area over here compared to the area in this side. So we look at the areas in these two sides. And the areas of these two sides are equal to one another. What does this tell us? It tells us that the probability of the photon being scattered in the forward direction is the same as the probability of a photon being scattered at backward direction. There is no preference. So if we had a photon, it's equally one interaction of Thomson, it's equally likely that we're going to find the probability of finding this photon in an angle between 0 and 90 is the same as the probability of finding this photon, the scattered photon between 90 and 180. Okay? Okay, so the differential cross-section per unit solid, per unit scattering angle is independent of this incident photon energy. This is also one thing, one aspect of Thomson scattering. You see in the formula that we looked at, showed you here, this differential cross-section does not depend on the photon energy. It does not matter if the photon energy is 1 keV or 100 keV or 1 MeV or whatever. There is no dependence. The cross-section, if the photon is going to undergo Thomson scattering, okay, this is the probability or distribution of the scattering, photons. So therefore, as we said, the probability of a photon being scattered in the forward direction is equal to that being scattered in the backward direction. Okay. Now we want to calculate what's the total electronic cross-section. So this is the differential, or what we need to do. Whenever we want to talk about total, after we differential, we have to integrate over all possible angles. So the easiest thing is we look at d sigma Thomson by d omega. So we look at this formula here, okay, this one here. And all what we need to do is integrate it with respect to theta for possible scattering angle. This is wrong, by the way. This should be pi. It's not pi over 2. Because the possible scattering angle is from 0 up to 180 degrees, which is pi. So this is a typo. This should be pi. Now, if we do this integration, we find that, okay, this is actually a constant value, which is given by 8/3 pi RE squared. And the numerical value for this is 0.665 bars. Okay, so this is something we have to remember, that the total Thomson scattering cross-section, this is electronic cross-section. So per electron, the total cross-section is 0.665 bars. Okay. So let's move on to something that probably you have heard of you dealt with, and that is Rayleigh scattering. So Rayleigh scattering is a little bit different than, well, conceptually is the same, but there are a few things that makes it a little bit different. In Rayleigh scattering, it is actually an interaction of a photon with an atom. It's not with an electron. It's with an atom. So the photon, there is an atom, okay, with electrons there, and then the atom somehow absorbs this photon, and then is going to emit that photon at a different angle. And the scattered photon actually will have the same energy as the incident photon. So whenever the scattered photon and the incident photon are the same, this means there is no energy transfer to charged particles or to an electron in this case. So the atom just absorbs the photon and then it scatters it at a different angle with the same energy, okay? That is Rayleigh scattering. It's not the same as Thomson scattering, and we were going to see why it's not the same. So the reason is because of this differential atomic cross-section. Now, if we want to calculate, suppose I have an atom of, let's say, carbon. Carbon has 6 electrons. And suppose we want to calculate the total cross-section. When we talk about atomic, is for the atom, is not for an electron. So if we go back to Thomson, this is the cross-section for a single electron. Now, in carbon, we have 6 electrons. So one would say, but the easiest thing to say, okay, then the atomic cross-section for Thomson scattering is just the number of electrons multiplied by the cross-section of a single electron. Now, if we look at Rayleigh, we find that actually the Rayleigh cross-section is not going to equal to the Thomson cross-section multiplied by Z. If it was by Z, then okay, there is no difference between Rayleigh and Thomson. This is just as that's with an electron. Now in this atom, we have Z electrons, so it's just multiplication of this. It turns out for Rayleigh, actually, it's, yes, this is the cross-section for a single Thomson, that formula, differential cross-section, but it's multiplied by what's called the atomic form factor. This atomic form factor depends on 2 things. Depends on the photon energy. Actually, 3 things. It depends on the photon energy, it depends on the scattering angle, and depends on Z of the atom. So if we look at this atomic form factor, this is how it looks like. This is a plot of the atomic form factor with respect to what we call the momentum transfer variable. This is X, which is given by sine theta over 2 divided by lambda. So if we want to know, for example, what value we need for atomic factor to use, first thing we're going to ask, what is the scattering angle? So we need the scattering angle, and we need to know what is the photon energy. From the photon energy, we can calculate the wavelength of the photon energy, and based on the scattering angle, we calculate the atomic form factor. From that atomic form factor, we look at these plots here. These are plots for different Z, different atoms, and then we obtain from it the atomic form factor, and this is, we put that value here. So now we need to repeat this process for every scattering angle. So I want to, if the photon energy is fixed, or we're talking about, we're interested to know the differential cross-section, atomic cross-section for Rayleigh for a given photon energy, then we need to modify the Thomson cross-sections based on the scattering angle, and we look also at the atom we're talking about. Now, the product of the two actually gives me an atomic cross-section. Here, this is an electronic cross-section, but the proper product of the form factor squared multiplied by the Thomson electronic cross-section gives me this atomic cross-section. Now, what happens is this what happens. This, for example, we look at hydrogen. This is a plot. So this thing, hydrogen, okay, there is one electron. Remember, look at when we looked at this. So this is for an electron. Now for hydrogen, we have one electron. So this curve here, this represents the Thomson electronic cross-section. But now when we want to plot the Rayleigh cross-section for hydrogen using this form factor, see what happens? Because this form factor will depend on the energy. So for 1 keV, look at how this differential cross-section looks like. It's modified. If we go for a higher energy, I think here it's 3 keV. Okay, this is how it looks like. And here it's for 10 keV. Just 10 keV, look at this. So we see a few things. First, as the energy increases, the area under the curve decreases. Okay, for hydrogen, I'm talking about hydrogen for the diamond. The area at 1 keV, this means the total cross-section of hydrogen, Rayleigh, okay, depends on the photon energy. And as that photon energy increases, we see that the area under the curve decreases. So that's the total cross-section. Another thing, what we observe is, okay, now we're looking at the forward and backward direction of scattering. As the photon energy increases, we see that the area, okay, between 0 and 90, now compared to the area between 90 and 180, this becomes larger. So that means the probability of the photon being scattered in the forward direction increases. Remember in Thomson, we said the probability of the photon being scattered from 0 to 90 is the same as photon being scattered in the backward direction from 90 to 180. Now in Rayleigh, it's different. We see that probability of the photon being scattered in the forward direction actually increases, becomes larger as the photon energy increases. So this tells us that Rayleigh is not the same as Thomson. Okay? It's not the same. Okay, so these are our equations. This is just here, the same thing, but if we want to calculate the atomic Thomson, okay, we just multiply Z by the differential Thomson. Now for Rayleigh, no, it's not like that. We still take the electronic Thomson, but we multiply by this form factor here, okay? And that gives us the Rayleigh. Now the form factor, it's squared, and if we go back, we see at very low angles, okay, here when theta is 0, so when theta is 0, x, we expect x to be very close to 0. So here we see that actually the form factors, they saturate or they approach the atomic number Z. Okay, so here this is for hydrogen, Z is 1, carbon, Z is 6, and so on. Here lead, Z is 82. Okay, so this means that the differential atomic cross-section, then it's probably is going to be a function of Z squared because it's the form factor squared.
دكتور عندي سؤال لو سمحت لخبطت
اتفضل.
شوية. الاكس اكسس عندنا هنا انجل ولا لام بيعتمد على اللامدا على الويف
لا
لينكس؟
هذه this is just a parameter, just some variable.
هو
يعني
مش
معروف
هاي
انه
الارقام هي انجل.
انه مومنتوم ترانسفير فاريبل. هذه عشان نحسبها ايش نسوي؟ نمسك هنا مثلا اعطيك مثال، اوكي؟ ليتس جو فور، عايزين نحسب لل1 كي في. ايش نسوي؟ نشوف كم الويف لينث اللامدا حق ال1 كي في. هذا نمره واحد. الحاجه الثانيه نشوف مثلا اللي احنا عاوزين مثلا وي لوك ات مثلا سي ات 90 degrees. 90 degrees يعني باي ثيتا ايكوالز تو باي اوفر 2. فنجي هنا ونشوف نحسب ساين اوف هتبقى باي اوفر 4 divided by lambda. هذا يعطيني البارامتر اللي هو الاكس. هذا البارامتر. نمشي للكيرف ايش هذا هيدروجين، نطلع بعد ما طلعنا الاكس نشوف في الاكس هنا، طبعا هذا اللوج سكيل، نمشي نشوف هذا الفاليو مثلا نفرض انه كانت هنا، اوكي معناها الفورم فاكتور از جوينج تو بي مثلا 0.08، خلاص نحط الفورم فاكتور هنا 0.08 سكوير، هذا يديني اللي هو الاتوميك ديفرنشال كروس سكشن. We
اوكي،
need
يعني
to repeat
هذا الفاكتور هو بياخد في عين الاعتبار الانرجي والانجل مع بعض.
exactly. اوكي،
ايوه تمام
عشان
تمام،
كده
شكرا.
ايوه، عشان كده تومسون مثلا احنا قلنا independent of energy. اوكي، هنا الديبندنس اوف انرجي هذا this part is independent of energy، لكن الفورم فاكتور actually depends on the energy، عشان x هذا المومنتوم ترانسفير هذا فيه الويف لينث، ف this depends on the energy. ف وعلى فكره الويف الاتوميك فورم فاكتور فور هيدروجين it could be calculated، طبعا لا تسالوني كيف it could be calculated for hydrogen. Okay, based on the wave functions والامور هذه، لكن it's very difficult to calculate it for مثلا higher or different atoms، لذلك this is more likely obtained from experimental data. Okay. فanyway، وعلى فكره في مثلا database اللي هو NIST I think they do actually have الفاكتورز هذه، لانه الجراف هذا when I created it it's actually from data، يعني data from NIST and so on. Okay. ف this tells us the bottom line is okay, Thomson's interaction with the electron really is not, it's yes, it's we have a scattering of the photon, no energy transfer, لكن it's actually not just, we cannot think of it as okay, we look at one electron and then multiply by the number of electrons, okay, that gives me the atomic Rayleigh scattering. Actually, when we do it for an atom, when the experimental data, no, it's not based on Thomson, it's based on this form factor here. Okay. But as the photon energy increases, we observe two things: the area of under differential Rayleigh scattering. Okay, what happens to it? This area decreases, at least for hydrogen. Okay, for hydrogen it decreases. For other elements, لا. For other elements, يعني مثلا let's look at here again. This area decreases because I'm not talking about Thomson. I'm talking about this is carbon. This is the atomic differential cross section. Again, as the energy increases, we see that the area under the cross section, atomic cross section, actually decreases. Okay. Another thing, as I mentioned before, is that the probability of forward scattering increases. Okay, as هنا مثلا عندنا 10 keV. Okay, 10 keV هذا يعني في diagnostic range. Okay, في الحدود هذه. فlook at actually where is this photon going to be scattered? We find that the photon actually, the probability that the photon is scattered backward is very low, is very negligible. Okay, the probability of this photon being scattered in the forward direction is really almost, it could be 90% or more. Okay, based on this. Okay, فما بالكم now when we do this for an MV, it's probably it's just going to be a very small يعني humpy over here. Okay. Again, these are the curves magnified: 1 keV, 3 keV, 10 keV. Okay. So so this is now the total cross section. So like Rayleigh, like Thomson, where we calculated, okay, the total cross section for Rayleigh, which is 0.665 barns. Now we can do the same thing for Rayleigh. Again, I'm doing the same mistake in the equations. This should be up to pi. It's not pi over 2. Okay. And of course, this integration probably can only be done numerically. So all what we need to do is to calculate what is the area under the curve. That's the whole idea of we integrate with respect to that, with the scattering angle data, and we get the area under this curve. That's the total Rayleigh cross section. And if we plot the total Rayleigh cross section as a function of energy, okay, so this curve, remember, we calculate for this energy, take the area for this energy, for this energy, and we need to repeat this for all photon energies that we're interested in. We get these curves here, okay, these solid lines. Okay, so here it is for hydrogen, carbon, aluminum, lead, and copper and lead. We observe the following thing, that the atomic cross-section for Rayleigh is proportional to Z squared. So if I look at hydrogen, this is 1. Carbon, 6. So I would expect that the cross-section, atomic cross-section for carbon to be 36 times that of hydrogen. Okay, because 6 squared is 36. And this is, for example, how we can correlate. If I know the cross-section of a material, okay, let's say aluminum, for example, if we know the Rayleigh atomic cross-section, we can calculate the atomic cross-section for lead, okay, just by taking this square. Now, probably we're all familiar with the mass attenuation coefficients of mass cross-sections, not the atomic cross-sections. I'm focusing now only on the atomic cross-sections. Once I finish these interactions, then we're going to deal with how to convert these atomic cross-sections into mass cross-sections, because that is more what we're familiar with, a mass cross-section, and then eventually a linear cross-section. But now I'm dealing at a microscopic cross-section, something related to an atom or to an electron. Rayleigh, one other thing, Rayleigh does not have an electronic cross-section. Why? Because it's an interaction of a photon with an atom. Okay, let's have that, understand this. There is no electronic cross-section for Rayleigh. It's an atomic. What's the cross-section for the atom? We cannot have what's the cross-section for an electron in Rayleigh scattering. That's wrong. We can have that for Thomson. We can say, okay, what's the cross-section for Thomson? And then we can also, from that, we can say, okay, what's the atomic cross-section for Thomson? Atomic cross-section for Thomson is just multiply the number of electrons by the cross-section of a single electron. But in Rayleigh, no, it's by definition, it's an interaction of a photon with an atom. Okay, so I hope that's clear. Now we go to this, our favorite. Is Marwa here? Is she with us, or she's not here today? Okay, she's not here today. Okay. So Compton scatter. Now I could actually spend one lecture, full lecture, or even more on Compton scatter, but I don't want to really make things boring for you. Okay? But we'll follow on the same steps, inshallah. So the first thing we need to define is what is this this interaction. Compton scattering is basically an interaction of a photon with a free, and I'm putting free on quotations here, with a free electron. Okay. There are no electrons in medium that are free. That's number one. All electrons are bound. And actually, I should put another statement here. This electron is stationary also. So the electron is sitting still, okay? Has no kinetic energy. And in reality, this is not true for electrons in matter. Electrons are always orbiting, you know, the nucleus, okay? But making these two assumptions makes us actually study, enables us to study this phenomenon, Compton scattering, okay? Because it's a very good approximation, and actually the kinematics of the interaction work very well for this area. But this is why I'm putting in these quotations free electron and stationary. I did not add the stationary word, but now it occurred to me. Okay. So the reason why this, because we have to understand electrons, they're not free in media, they're bound. And another thing is that electrons, they're not sitting without any kinetic energy. They actually orbit the nucleus. They actually in motion. Okay. So in Compton scattering, we can think of the electron of being actually stationary, no kinetic energy, and then we have an incident photon coming to this electron, and this photon is then going to be scattered, like Thomson, like Rayleigh. But the energy of this scattered photon is actually less than the energy of the incident photon. Actually, here is the scattered photon. Okay, so we have this incident photon and this electron, the scattered photon. If it had the same energy, this defines Thomson scattering. If the target is an atom and we have the same energies, okay, incident and scattered photons, this is Rayleigh scattering. Now in Compton, the energy of the scattered photon is actually less than the energy of the incident photon. Now, this means that there is going to be some energy being transferred to a charged particle, to the electron. So this is one of the interactions, okay, it's important for us when we're dealing with doses. Rayleigh does not deliver any dose. If all the photons undergoing interaction with medium with Rayleigh, no dose is deposited. We need to first transfer energy to an electron. And this scattering interaction is actually the first interaction on our list that actually can do this. So the energy transfer of the electron, very simple. Conservation of energy. This is the energy of photon scattered with a lower energy. The energy difference is going to be given to the electron. This is the energy transfer to the electron. It's equals to the incident photon energy minus scattered photon energy. Okay. Any questions? So now we're going to go into some serious stuff for physicists. Now, the kinematics of this interaction, we can study it. We can say, okay, this is an interaction. It's an inelastic. By the way, sometimes it's called an inelastic scattering. Rayleigh, on the other hand, is called elastic scattering. Why elastic? Because we're looking at the photon. If the scattered photon energy equals to the incident photon energy, we say this interaction is elastic. So Rayleigh, sometimes in some references, you might find the word, they don't use Rayleigh, they use elastic scattering. So always think of Rayleigh, because the incident photon and the scattered photon, they have the same energy. Now in Compton, in some references, they call it inelastic scattering. Why? Because the incident photon and the scattered photon do not have the same energy. So, okay. So now we can do some of the kinematics. We can say, okay, conservation of energy. We look at before always conservation. When we have an interaction, we look at what happens, what's the energy before the interaction, and then what's the energy after the interaction. So before the interaction, we had a photon with an energy hν, and we had an electron, and the rest mass energy of the electron is mEc². After the interaction, what happened? We had a scattered photon with an hν prime. That's the energy of it. It's with a lower energy. We have an electron, so we have the rest mass energy of the electron is still there, and we have the kinetic energy of the electron. So anyone has a problem with this equation? This is initial energy before interaction, and this is energy after the interaction. Now we can also look at the conservation of momentum. So let's take in this axis here. So when we deal with conservation of momentum, we can, look at the components in each axis, in the x-axis and the y-axis. Since it's a scattering event, we must have this concept. So we have the photon momentum equals to, so we look at this, the incident photon momentum, we look at this is the momentum of the scattering, momentum of the scattered photon, then we look at the x component. If the scattering angle is theta of the photon, then we take the momentum of the scattered photon multiplied by cosine of this angle. And the electron, since now it's set in motion, it's taking some energy, so it will have momentum. So this is the momentum of the electron. Again, we need to take the x component of the momentum of the electron. And in general, this recoil angle, or the angle at which the electron is going to be ejected at, is not going to equal to the scattering angle of the photon. So that's why we use another symbol, we call it phi. So we want to talk about conservation of momentum. Initially, the electron is at rest, so it does not have any, it did not have any momentum. We only had momentum of the incident photon. This is the initial momentum of the system. And the final momentum of the system, now we have a scattered photon. It has a momentum. We take a component along the x-axis, and we have a momentum of the electron. We take a component in the x-axis again. We do the same thing now. We look at conservation of momentum in the y-axis. So initially, we did not have any momentum in the y-axis. This incident photon is just traveling in the x-axis. Electron is stationary, so no momentum in the y-axis. So after the interaction, what happens? This electron will have a momentum in the positive x-axis equals to the momentum of the electron multiplied by sine of phi, that's the angle, ejection angle of the electron. And we have in the other side, we have for this scattered photon, we have the momentum equals to, actually this should be sine. You see, this is a typo, so sometimes I'm not careful. This is sine, actually, because we're looking at sine of the angle theta. Now, the momentum of the photon, this is basically h over lambda, or we can write it as h mu over c. This is a famous equation. I don't know if you're aware of this or not, but this is, we're going to use actually this equation more, especially in when we talk about pair productions. So this is basically the total momentum of a system, of a particle. This E is the total energy. Sorry, it's the total energy. The rest mass plus the kinetic energy squared equals to the rest mass energy squared plus momentum multiplied by c squared. That's a famous relativistic equation. So for photons, just to show you how, if you know this, you can get these formulas immediately. So for a photon, the rest mass energy of a photon is 0 because it does not have mass. So we get the energy of the photon equals to the momentum multiplied by momentum of the photon multiplied by c, the speed of light. So the momentum of the photon equals to the energy of the photon divided by c. And now we can do the same thing for an electron. If an electron has a certain kinetic energy, then the total energy of the system of this electron is the kinetic energy plus the rest mass all squared equals to the rest mass squared plus Pc squared. These equations, if we use these equations in addition to these equations here, then we come up with very interesting results. I don't know if you have done this derivation in your career or not, but we were required actually to do this during our master degree. We had to derive this from. So it's good to actually derive it one time and then that's it. Then you trust, okay, these equations are correct. So what we get after we manipulate and so on. What we're interested to know, just for information, we're interested to know, okay, what is this energy, scattered energy? We are interested to know this, okay? This obviously will depend on the scattering angle theta. We're also interested to know what is the kinetic energy given to the electron. Because we are going to use that in some way, okay, to calculate what's the dose in a phantom. So if we entertain ourselves with the mathematics and do the derivation, we get this famous equation for the Compton wavelength shift equation. This is, so the shift in the wavelength scattered photon and the primary photon, this equals to some constant multiplied by 1 minus cosine theta. Okay? This constant is called the Compton wavelength of an electron and is given by this formula. It has a value of 2.024 angstrom. So those who are taking board exams, sometimes they might actually state, okay, what's the Compton wavelength is equal to, they give you some values, 0.511 MeV, some, okay, whatever. So it is actually 0.024 angstrom, or in SI units, it's given by this value. And it's actually given by these, it's a constant. H is Planck's constant, is it, okay, and Me is the rest mass of an electron, of the mass of an electron, and C is the speed of light. So just plugging the values here and do the conversions, we get the Compton wavelength. This basically tells us that if I have a photon, if I know its wavelength, then the wavelength of the scattered photon is going to be shifted, is going to differ from the wavelength of the incident photon by this formula here. We need to know what's the scattering angle. But really what is important for us are these two equations. Because now in our field, we're not interested in spectroscopy, and we're interested more in, okay, how much energy was given to the electron. Energies, that's what's really important for us. So the first formula is that the energy scattered fraction. This is basically what's the fraction, or it's the ratio, we can think of it as the ratio of the incident, the scattered photon energy to that of the incident photon energy. This ratio, we're going to call it the energy scattered fraction. How much of that energy, of this incident photon energy, percentage-wise or fraction-wise, how much of that was actually scattered in a photon? If that factor is 1, okay, then nothing has happened. And it's given by this formula here. 1 plus epsilon 1 minus cosine theta. Now, how about the energy transfer? That is even more interesting for us. That's the energy transfer fraction. Well, it's just 1 minus the energy scattered fraction. So if you do this, then we get that the energy transfer fraction is basically the energy of the electron divided by the photon energy. Think about it. We have a photon energy. We want to know what's the percentage of that energy was given to the electron. That's what we mean by energy transfer fraction. So it's given by this relationship. Epsilon 1 minus cosine theta 1. So when I memorize, I still memorize these formulas, till today. All what I need to memorize is this thing. 1 plus epsilon 1 minus cosine theta. If we're talking about scattered photon, we put here 1. So we put this one here. If we're talking about electrons, we take this part, we put it here. That's all. This is the formula. Now, this epsilon is basically the photon energy divided by 0.511. Okay. So these are important formulas, and we can use it to calculate things, or to even. I will show you, demonstrate now. So based on that formula, we're looking at this first formula here. Okay. We want to calculate, okay, what is, for example, I have, we can directly calculate if the scattering angle, let's say it's 90 degrees, and my incident photon energy, let's say it's 1 MeV, then we can immediately calculate what is the energy of the scattered photon based on this formula. Straightforward. And what is the energy of the transfer to electrons? Now, if we change the photon energy, we're still going to keep the scattering angle 90 degrees. Okay, but now I want to see what's the fraction scattered photon. If, for example, now the energy of the photon is 10 MeV. So what we need to do, we need to, again, repeat this formula here. Okay, but instead of incident energy to be h mu equals to 1 MeV, now it's going to be 10 MeV. And theta is still going to be 90 degrees. We can repeat this process, do it for 1 keV, 10 keV, 100 keV, 1,000 MeV, and so on. Okay. So we want to know, for example, what's the limit of that, of the energy of the scattering photon. This is what we call the saturation scattered photon energy. And it has a very nice application that I will show you now. So we want to know, for example, for a given angle, theta, what is the energy of the scattered photon if the incident photon approaches infinity? It is given by this formula here. So let's look at a nice application. Suppose we are interested in the photon being scattered in the, or being backscattered at 180. The question is, what is the energy, the maximum possible energy of that backscattered photon? Imagine, so let's shift so that you understand a nice application of this. Suppose we have here, okay, we have a source of photons. This is here some shielding. Okay. Basically, it's a way to say, okay, I want the photons to always be shooting in this direction. Okay, this will be the energy of the photon. Now, we have, this is in a lab, think of it in a lab. Okay, what we are interested, we want to know, for example, what thickness we need to have in order, for example, to do some shielding, to reduce, for shielding calculation. So definitely what we need is we need to know what is this energy of the photon, because based on this energy, then we are going to determine, okay, what is the linear attenuation coefficient, and then based on that, we will determine, okay, how much thickness we need to attenuate the beam and so on. So this is going to depend on this photon energy. Now, the question I have is, we are interested to do the same thing, but now for a wall on the opposite side. So still, the source is shooting photons in this direction. Okay, not here. So we want to know what thickness, okay, we need to actually use for this wall. So the first question is going to be, what energies of photons are going to hit this wall? So we want to know this energy of photons. This is incident photon, this is in this direction. So these photons can only come from backscatter. Okay. So undergoing, so if it's undergoing Rayleigh, oh, Rayleigh is beautiful because these photons will go, we said it's more in the forward direction. We have no problem. But photons that are backscattered, this will be probably from Compton scattering. If these photons are going to undergo photo effect, excellent. Because photo effect, as we'll talk about it maybe next week, all of the photon energy is given to electrons. So the photon disappears. We're not worried if the photon undergoes photo effect here. We're not going to have a scattered photon here. But the scattered photons in this backward, in this wall, will come from Compton scattering. So the question is, what is this backward energy of the backscattered photon? So the formula is h mu, okay, equals to, we can put it like this, h mu over 1 plus h mu over n c squared, 1 minus cosine theta. So theta is 180. This is going to, we're going to have 2 over here. It's going to be 2. Okay, because cosine theta is -1, and 1 minus 1 is going to give me 2. So this is simple. If we have a 1 MeV, okay, 10 MeV, we can always calculate this h mu pi. But when we want to construct this wall, we would say, okay, probably it's good to see, for example, maybe we want to be smart. We want to construct this wall maybe one time only. So if I change my energy of the source, okay, maybe it's not, I will definitely need to change the thickness of this wall for sure, because the energy will be different, but better at this wall here. If we do, we want to see, so basically we want to look at the limit of this energy as the incident photon goes to infinity. And if you do this for theta equals to pi, okay, 180 degrees. If you do this, you will find that the maximum possible energy equals to this. This is what it tells us that, okay, the maximum possible, even if this incident photon has an infinite energy, the maximum possible backscattered photon cannot exceed 0.255 MeV. So if I want to look for attenuation coefficients, I really don't need to look for, I don't care about this photon energy. I really don't care about it. It's sufficient if, okay, we're going to assume that this is the maximum possible energy is going to hit this wall. It's sufficient to go and look for linear attenuation coefficients for 0.255. If this energy, and this is for an infinite energy, remember, it's for infinite. So we know that the backscattered photon are always going to be less than 0.255. This, we can apply the same principle. I hope now this is, it's a nice application. So if, for example, we're looking now something on the sides, okay, we'll say probably the photon, this photon, when this happens, we're going to get a scattering at 90 degrees. Okay, so I need to worry about that. Definitely, it can be at a higher angle than 90, but 90 probably is the maximum. You will find that the maximum, if this is infinity, then the maximum possible photon energy scattered at 90 degrees is going to be MeC, or 0.511 MeV. So it's sufficient if I want to construct the thickness of this wall, and okay, the maximum energy of photons being scattered or will reach this wall will have an energy of 0.511. Then probably it's good to go and look for the attenuation coefficients for 0.511. That will be sufficient. Okay, I hope this illustrates this point. So this is the formula. Okay. And here, this is the plot. Okay, so if theta equals to pi, and we are plotting, here we're plotting the scattered photon energy versus the incident photon energy, we will see that, okay, this curve will saturate or will approach a certain value. This value, or the limit, okay, it's basically what we're doing. Is this formula. The limit is going to be MEC squared divided by 2. Cosine theta equals to pi -1 when pi equals to theta equals to pi. So we get MEC squared over 2. Now, if we're talking about a different angle, like this side is scattered toward 90 degrees, then theta equals to 0. Theta equals to 90. Cosine 90 equals to 0. So the limit, or this saturation scattered photon, or the maximum possible, let's say, is going to be 0.511. And this is this curve here. We see that it saturates at MEC squared. Okay, I hope this is clear. These are very important concepts because I found, for example, even for ABR related questions, in ABR, we see, for example, some questions. They will ask, okay, what is the energy of a 10 MeV? What is an energy of a backscattered photon for a 10 MeV photon undergoing Compton scattering? So immediately we know this backscatter is 0.255 MeV because the incident photon energy is very high, as if we are approaching infinity, 10 MeV. Okay, and if we look at this curve, okay, it's roughly going to be 0.2. It's going to be a little bit less because 0.255 is when the photon energy is infinity. So, but roughly this is going to be around that. Okay, this is a common question I've seen in AVR and in matrix. Okay, you could calculate it based on this on the formula. That's fine. You can do this. So, for example, I think in the answers you will find 0.511, you will find 1 MeV, you will find 10 MeV, and so on. But it's Compton, the trick. Okay, it's a Compton interaction. If it was Rayleigh, for example, no, the backscatter would be the same. But for Compton, no, the backscatter can never exceed 0.255. So if Ali came and thought, no, okay, I have a backscatter photon, 10 MeV, and the backscatter photon energy is 2 MeV, I'll tell him, okay, backscatter, that's wrong. It can never exceed 0.255. If he said it's 0.3, 0.4, it's wrong. Can never exceed 0.255. Okay, I hope that's clear. Any questions? So now the energy of the backscattered photon, so we're not talking about the limit. That one is the limit. This is, we're looking at the limit. What happens if the photon energy increases? What's the energy of this backscattered photon? But for any photon energy, we just apply the formula and we get this is the backscattered photon. So this is actually the minimum possible. Okay, energy of the photon. So if a photon, for example, undergoing a scattering at, let's say, 40 degrees, it will have a higher energy. The scattered photon will have a higher energy than a photon undergoing scattering at 90 degrees. And it will have a higher energy. Or let's say the photon scattered at 130 is going to have a lower energy than a photon being scattered at 90 degrees. And so the lowest possible, or the lowest energy, this is why we're calling it here H mu prime minimum. This will happen when the scattering happens at theta equals to pi, and it's given by this formula. I know the value for 1 MeV is around 0.8. Okay? And at 100, it is 1, almost 1. So imagine 100 MeV. Okay, we're looking at, sorry, this is we're talking about here. Okay, this curve here. This is the minimum, sorry. That is different. So, because this is the important curve, this is what I memorized, the energy transfer. But, so what I was talking, now this one, the maximum energy transfer, how much energy is going to be transferred to the electron? And at which scattering angle, this energy is going to be maximum. So the energy is going to be maximum when we have a scattering at 90 degrees, 180 degrees. At theta equals to pi, this gives me the maximum possible energy transfer to an electron. And this is the curve that I always memorize. It's this one. So at 1, if the photon energy is 1, then the maximum energy transfer is 0.8. Just look at plugging in these values here for the formula. And at 100, it's going to be almost 100. Okay, this is the fraction. So 1 is 1 times the photon energy. At 1, it's 1 times 0.8, so it's going to be 0.8 MeV. And if we go for lower energies, okay, the amount of energy transferred to the electron is actually, or the fraction percentage is actually decreases. So we see that as the photon energy increases, actually the photon takes more of, the photon fraction energy-wise. Okay. So for the backscatter photon, it's 1 minus. So this plus this will always equal to 1. So here, the maximum scattered photon energy, obviously, this is always going to be equal to the incident photon energy. This is when the scattering angle is 0 or no interaction happens. So when theta is 0, then that's when we will have the maximum energy of the scattered photon, and we will have the minimum energy or almost zero. It's zero actually in this case, and minimum zero or minimum energy transfer to the electron. So now that's the kinematics of Compton scattering. The next thing is we also have to think of, okay, the preferences, in terms of angle. So if I have a photon being scattered, the scattering can happen at all of these angles from 0 up to 180. But is there a preference? Are these angles all probable to one another or not? Or like Rayleigh, Rayleigh, we see that, no, actually something happens. Okay, preference, more in the forward direction than backward and so on. So this is when we start to look at the differential electronic cross-section for Compton. Since Compton, as we defined it, it's an interaction of a photon with an electron, then we can talk about an electronic cross-section. This was actually derived by Klein and Machina, where they showed actually this differential cross-section. I'm going to call it Klein-Machina because Compton, I'm going to make it a bit different. This is for Klein-Machina. It's basically for a free and stationary electron. The differential cross-section, electronic cross-section, equals to that for Thomson. See why Thomson, I like to look at back into Thomson. This is the differential cross-section for Thomson. But now they have a form factor or a correction factor to modify this Thomson differential cross-section. Like the Rayleigh, we had the atomic form factor squared to modify the differential cross-section for Thomson. Now for Klein-Machina, it's actually, we have this function here, F Klein-Machina. Okay, and it's a function. It's a horrible function. Okay, believe it or not, in one stage in my life, I actually had to memorize it. And I got a question in the exam on this, but basically calculate, the Klein-Machina form factor for angle for H mu equals to 1 MeV and scattering angle equals to 45. So if you know the formula, you will know it. But this is the plot of this Klein-Machina form factor, okay? As a function of angle, and each curve represents an energy, or actually H mu over MEC squared. What we see from here, the following. At low energies, so we have this is 0. So the F Klein-Machina is equal to 1. Essentially means that, okay, for the differential cross-section at very low energies, it's equal to that for Thomson. This is going to be 1, irrespective of the scattering angle. It's this curve. Okay? This is F Klein-Machina for 0, for very low energies, okay, for 0, it's equal to 1. So this factor for H mu equals to 0 is always going to be equal to 1. So the Klein-Machina cross-section, differential cross-section, equals to that for the Thomson. Remember the curve for the Thomson? We had these two equal to one another. Okay, it's this thing, okay, or this thing, that the solid angle. But I always like to look at it in theta. Okay, so at very low angle, low energies, the Compton differential cross-section equals to the Thomson. So now as the photon energy increases, we start to see something interesting happening. We start to see for 0 angles in the forward direction, still it is 1. But as the angle increases, you see, okay, this correction factor or this form factor has this form. Okay? And essentially, what does this mean is that we are going to, this is the differential. Okay, this is, yes, I want to show you this stuff. So this is hydrogen. Hydrogen, 1 electron, Thomson. This is the differential cross-section. It looks like that. Now, the Klein-Machina cross-section, what happens is we start to see this part in the backward. This area starts to decrease because of the Klein-Machina. Okay, whereas this part here still remains the same. This is the same. Okay, it decreases a little bit, that's fine, but it will match this. But here, look what's happening. We're taking more of in the backward direction. Okay, this is Essentially, what this F-Clinachina does. See it here, we are decreasing more the Thomson in the backward angles. Okay. This is what's happening. Another thing is the overall area. Okay, remember, this if I look at the area of under this, the total cross section, this is constant for Thomson, it's 0.665. But what happens as we increase the photon energy, then this F-Clinachina will have an effect on the cross section, the total cross section. It's going to decrease it. So the limit for Clinachina, the total cross section, essentially when theta equals to 0 at low energies, it's going to be 0.665. It's going to match that of Thomson. But as the photon energy increases, this cross section, the total cross section, is going to decrease. Okay, so this is again, this is the differential cross section, but with respect to the solid angle. Okay. This curve is for Thomson, and what's happening? Okay, because of the F-Clinachina, we are reducing the area, all overall area. But if we take any curve, we look at the area in the forward direction compared to the area in the backward direction, and we find that as the energy increases, okay, the photons are being scattered more in the forward direction. This has some implications in radiotherapy. Remember, if you looked at this backscatter function, or if we looked at the peak scatter factors, and many other things in dosimetry, we can explain, for example, why the peak scatter factor actually decreases with increasing energy. We can explain, for example, why, for example, the PDDs, the dependence on field size, why does it decrease actually when we increase the photon energy? Things like that, because now we're considering, okay, the direction of the photons being scattered in the fact. As the energy increases, these photons will be scattered more in the forward direction. Okay? So now we want to really dig into and get actually what is the quantum scattering. F-Clinachina, the electron is free and the electron is stationary. So if we had an energy that's in a few keV, or let's say we have, let's suppose we have a photon of 50 keV, and we have an atom of lead. We know this photon, Compton, cannot interact with the K-shell electrons. And probably it cannot interact with L-shell electrons for some angles, maybe. Okay, we just have to calculate the values, because it has to, when it interacts with a given angle, it has to give an energy to the electron in order to, this interaction can happen. So a 50 keV Compton cannot have an interaction with K-shell electrons for lead. But the Clinachina formula assumes that the electron is free. We are now interested to calculate the atomic cross-section. So the atomic cross-section, assuming electrons are free, okay, we take the Clinachina for one electron and then multiplied by the number of electrons of the atom. So this is the atomic Clinachina. If this is total, this is going to be total. End of story. We just need to multiply it by the number of electrons. But because we have these binding effects that might come into play, especially if the photon energies are low, then we need, this is not going to give us the correct result. So we need to talk about the Compton atomic cross-section. This is basically this Clinachina differential cross-section multiplied by a factor. It's called the incoherent scattering function. This thing. Something similar to the form factor, but it's actually reversed. The curves are a little bit reversed. Remember the form factor? We had the curve here, they saturate and then they drop like this. But we have for Compton, okay, the cross section. This is basically, you can think of it more like a incoherent scattering function. It's incoherent, it's similar to Compton. So Compton scattering function is basically a correction factor to take into account the binding effects of the electron. And obviously, this is probably going to have a role when we're dealing with low energy photons, not for high energy photons. Okay. And as we're going to see later, Compton is dominant in the megavoltage range. Then this probably has no, effect on our range in the megavoltage. Probably in the kilovoltage, yes, but not in the megawatt. I'm going to illustrate this. So again, this is again a function of this momentum transfer variable x, okay, which we know now how to calculate based on this. So for every scattering angle, we need to calculate sine theta over 2, and we calculate the wavelength of the incident photon energy, get the momentum transfer variable, and then look into the curve and get, okay, the value, and that value we're going to plug it here. We do for a different angle, for a different energy, and so on. And these are the curves that we get. So the Kleine Schiene are these solid curves. Okay? These solid curves. But now when we add for hydrogen, of course, because it's one electron. Now, when we add the binding effects of electrons, or we incorporate the incoherent scattering function, see what happens? This part in the front here, okay, the cross-section actually decreases. Why is this? I just want you to think, why are we having that? Because this is the scattering angle. The scattering angle is very small. So the energy that it's going to transfer to a free electron is small, actually. It's not a backscattered photon, it's something small angle. Now, if this electron is bound, probably it cannot participate. It cannot actually undergo the interaction because the energy that the photon is going to supply is actually less than the binding energy of the electron. And this is why this is the effect of the incoherent scattering function. This is here, I think, for a 10 keV curve. Let's look at a 1 keV curve, a lower energy curve. Look at this. This is the 1 keV curve. This is 1 keV assuming Kleine Schiene. Electron is free. In reality, when we take the binding effects, okay, the electron probably cannot receive that energy for a 1 keV. The energy that the scattered photon is going to give to the electron is less than 13.6 for some angles. Then, okay, this cross-section is going to decrease like that. Okay, look at this. So it starts very small because of the bonding effects of the electron, and then as the photon energy increases, we start to get, okay, we're going closer to the Kleine Schiene. Okay, and then as we go to higher energies, see, this is 0.1. I don't think there is even any difference, for 100, if the electrons are bound or not. For hydrogen, it's irrelevant. 13.6 electron volts, that's the binding energy. We're talking about 100 keV. So the electron, if I give it a very small fraction, it's going to no problem at all. 1 MeV and so on. So the Kleine Schiene, yes, it's a good model, remodel, because the binding effects of the electron actually are negligible for high energies. So it's good to assume that the electron is actually free, no problem. This is the same situation, but now we're talking about lead. So lead, this is 1 keV. This scale, okay, remember, at low energies, the F Kleine Schiene is very close to 1. Okay, and we would expect that the differential cross-section for Compton matches that for Rayleigh, for Thomson, multiplied by Z in this case, and we're going to have the photon being scattered in the forward and backward direction, probably going to be the same. So if we look at 1 keV curve, this area and this areas are the same. Now, if we take the binding effects into consideration now, okay, this 1 keV transforms to this curve, 1 keV. Because the electrons, 1 keV, how many electrons in lead can it actually interact with? Very few, only those at the end. So it's very, very small. Now, if the photon energy increased to 10 keV, okay, the curve starts to increase. We can actually, it's possible to interact with this. And as we increase the energy until we go to the MeV range, so the MeV will start to get back. This is one MeV, kleine Schiene, and this is one MeV with incoherent. And then if we go to, sorry, 0.1 MeV, so this is 100 keV, this is one MeV, we start to see that these curves now are going to match one another. So that's why, and this is basically where we really deal with content, or its dominant. I'm coming from a radiotherapy background. So that's why kleine Schiene model works well for us in our energy range. This is now a plot of the total cross-section. So it's that area. So this is the kleine Schiene. The dotted line, it's basically the kleine Schiene. And it saturates. Saturates to which value? Here for hydrogen, this will saturate to 0.665 at very low energies. That is the total cross-section for Thomson. Now, for carbon, it's Z times 0.665. That's the kleine Schiene. The dotted line is the kleine Schiene. It's just for one electron multiplied by the number of electrons. For lead, it's going to be 82, because it has Z equals to 82 for lead, multiplied by 0.665 watts. That is where it saturates. Now, if you include the binding effects, okay, see what happens, especially at low energies, is not going to match that. Actually, it's going to, okay, the cross-section now is going to be lower because the photon cannot interact with these electrons, some of these electrons. Okay, clear, ya shabab? Now, in megavoltage range, 1 MeV to 10 MeV, look, this binding effects, negligible. The kleine Schiene and the Compton with the binding incoherent scatter function, for binding effects, doesn't matter because the binding energies are keV or even less. So here it doesn't matter. The electrons then appears for a photon, they're free, they're not bound. Okay. This is an important graph. Dr. Podgortuk used to tell us, this is the graph. He calls it the graph. Okay, very important. Now, we have actually the equations to calculate what is the energy transfer to an electron if we know the photon energy and if we know the scattering angle. Okay, that famous formula here. This one here on the bottom. Because now I'm taking you towards dosimetry. Okay, that's our aim from now on. So we need to figure out what's the energy transfer to electrons. So if we know the scattering angle and we know the incident photon energy, we can calculate what is the energy transfer. Good. So I have a 1 MeV photon, and we want to calculate how much energy is going to be transferred to electrons for a 1 MeV photon. The issue is, okay, this 1 MeV can undergo scattering 0 degrees, no energy transfer, 1 degrees, 5 degrees, 10 degrees, 90 degrees, 130 degrees, 180 degrees. 180 degrees will have the maximum energy transfer fraction. So we need to calculate what is probably the average energy transfer. If a 1 MeV photon interacts, on average, how much of its energy is going to be given to the electron? That will depend on the scattering angle. So what we need to do, we need to ask ourselves, what's the probability of the photon being scattered on this angle? Is it equal to one another? Is it independent of the scattering angle? Actually, for Compton, no. It's distant, right? So the differential cross-section tells us, it gives us information about the probabilities of the scattering angle. Here, for example, if we have a low energy, okay, 55 has the highest probability, or this is 125, I think, or 125, and 55 has the highest energy. Okay, but something scattered, let's say at 10 degrees, it will have a lower probability, and so on. So if I want to calculate what is the average energy given to an electron for the 1 keV, we need to take these probabilities, okay, of each angle, possible angle, multiply the energy for that particular angle, and then average it, average out things. This is written in this form, okay? This is exactly what I have explained. We take this differential cross-section and we multiply it by the transfer fraction, okay? We integrate this over all solid angle, and then we divide by the total cross-section. This is just the total cross-section. Now, this has a multi-term, actually. I think in the book, where this actually is derived, okay? Or the formula is shown, and it's a long formula. But we're not going to memorize that formula. We're going to memorize this graph. That formula actually gives us the energy transfer if we multiply by the cross-section, or energy transfer cross-section multiplied by the cross-section. It gives us this mean energy transfer fraction. This is important. It's the graph, and I would advise you to actually, look at this graph, memorize it. You can then do a lot of things. Amazing. So basically, this graph, do I have? Yes, I want to show you this. So it has this sigmoid curve shape, okay? And it gives me immediately what's the average energy transfer fraction. So for example, for 1 MeV, on average, the electron energy will be 0.44 MeV. This is if we average all of the scattering angles. Now, if the photon energy is 10 MeV, then on average, the electron will have an energy of 6.8 MeV. This is the fraction. This is fraction with respect to the photon energy. So we need to multiply this value by the photon energy. If we're going for 100 MeV, okay, then on average, the electron energy will be 0.8 of the photon energy. So it's going to be 80 MeV. So now we can, and here these are for known energy. So give me a beam energy, and then we can estimate, okay, based on this energy, we're looking at probably, we're going to assume all the interactions are going to be constant. Later on, we're going to understand why, especially in radiotherapy. Then, okay, that is actually on average, this is the energy of the electron, or the average energy. We will have electrons with higher energy, and we will have electrons with lower energy, for sure. But the average energy of these electrons is going to be 0.44. This is important later on when we want to look into cavity theories. We want to calculate what is the dose. We need to know what is the average energy of electrons crossing the cavity. Okay, so we will use this. That's why it's called the graph. It's very, very, very useful. Okay, so these are anchor points. It has this sigmoid shape, and then just once I know these anchor points, then we can determine, estimate. Okay, if I have a 5 MeV, so we'll go 5 MeV is probably here, so it's roughly maybe around 0.6. Not a bad estimation. So 5 times 0.6, how much is that? It's more than 3, right? It's more than it's about 3 MeV, a little bit. Because 0.5 is 2.5, so this is going to be higher, a little bit higher. So roughly around 3 MeV. What we observe from this graph is that the higher the energy, the more actually of the photon fraction energy is given to the electron. Here, only 2%. So imagine if I have 10 keV, only 2% of the photon energy on average is given to electrons. Whereas if we have 100 MeV photons, okay, we're giving 80% each interaction, or on average, the interactions will give electrons 80% of their energy. See the difference? So this is the graph. This is now the Kleine-Scheiner cross-section. Also, these are things. This is the Kleine-Scheiner. So the electron is free, as I told you, at low energies. The Kleine-Scheiner form factor is 1. So the Kleine-Scheiner and the Thomson are essentially the same. And we get the curve. It should be 0.665 Mars. Should match. Okay. At 1 MeV, the value is 0.2. So sometimes, okay, what's the cross-section for Compton? 1 MeV, it's about 0.2. And at very high energies, you see, it's even point. So usually I go to 100. 100, I would say it's roughly around 0.01. So this is the total Compton cross-section for Kleine-Scheiner. This is exactly the same as this curve. But now we're going here. Okay. Because this is hydrogen, so it's the Kleine-Scheiner. And now we're going to some useful quantity. We call it the the atomic transfer cross-section. So it's basically defined as the cross-section multiplied by the energy transfer fraction. So for 1 MeV, this value from the previous curve, this is 0.44. Okay, so 0.2 times 0.44, it's going to be a little bit less than 1. See, the value is here, less than 1. So this curve, the transfer, this is the Compton electronic transfer, how we call this, mass energy, okay, Compton energy transfer electronic, it's the electronic transfer coefficient. Okay, it's actually. Now, why we have this gap? Why? Because of this thing. See, only 2%. It's the product, right? Only 2%. So the values here, this value, the transfer fraction, this is going to be only 2% of this cross section. Okay? And this quantity, actually, when we do the mass energy transfer coefficient, that is very important when we want to calculate the curve. Okay. So this is a conclusion. Compton scattering, we have the Compton atomic cross-section is basically is proportional to Z. It's like the Kleine-Scheiner, it's proportional to Z. Okay, so it's proportional to Z. This is the atomic cross-section, not the mass attenuation coefficient. Atomic cross-section. And this cross-section decreases with energy when binding effects are neglected. Okay. Another thing is that the probability of forward scattering increases with photon energy. And the energy transfer fraction increases with photon energy. So that's the graph. Here is a comparison. Here, these are Compton atomic attenuation coefficients for the same elements, hydrogen, carbon, aluminum, and lead. And the difference, if we take one energy from here to here, it's the Z. So here, this is the value is 6 times this. Aluminum is 13, this is 13 times of hydrogen. Lead, this is 82 times hydrogen. This is, remember, it's a log scale. If we go to the Rayleigh, it's Z squared, the atomic cross-section. So carbon is 36 times that of hydrogen. And lead is 82 squared that of hydrogen. It's complete. The dependence on Z for the atomic is Z squared, whereas for Rayleigh, whereas for Compton, it depends on Z. Now we said here for Rayleigh, this decreases roughly as 1 over the energy square. Okay. Compton, we don't have really, we know it decreases, but It's not like 1 over h mu of the energy answer. As we just say that it is the cross-section decreases with photon energy. Okay, so I'm going to stop here now. And inshallah, next week we will have one more session. And we will deal with the photoelectric effect, triplet production, pair production, and photonuclear interactions. Okay, so I'm going to stop the.